Okay, this question asks to rank these three nucleophiles from strongest to weakest in a protic solvent. I don't know that the protic solvent plays any real issue here. What does play an issue is going to be two things. Number one, we have an O minus versus an S minus. And so we'll have to determine what relationship that is and which one is the stronger nucleophile. And then we have this primary alkoxide, and an alkoxide is just a deprotonated alcohol, versus this alkoxide, which is attached to a tertiary. And so what would the role of that be? And so let's deal with the primary versus tertiary issue first. So in this reaction, we're going to take a nucleophile, we're going to have it react with a carbon attached to a leaving group. The nucleophile is going to substitute for the leaving group, which in this case we could think of as maybe a halogen ion, or a halogen atom becoming a halogen ion. And so in this case, the issue is how would a primary nucleophile differ in reactivity from a tertiary one? Well, to answer that question, we would really want to think about the alkyl halide. What kinds of alkyl halides react fastest in an SN2 reaction? Well, since backside attack is the major, or is the mechanism for SN2, then the steric hindrance around this carbon is what's going to play the most important role in determining the reactivity. And so remember that in SN2, actually a methyl group attached to the halogen would react much faster than a primary, would react faster than secondary, and tertiary alkyl halides don't react in SN2 reactions. So that's based on the steric hindrance around this carbon. Less steric hindrance, faster SN2 reaction. Well, I would apply that same principle to the nucleophile. What kind of nucleophile is going to react faster in an SN2 reaction? One that is going to be less hindered. And so which nucleophile is that up here? Primary versus tertiary. And so the primary halide of these two are going to react faster than the tertiary alkoxide. So again, it's totally based on steric hindrance. The primary is less hindered, and so that's going to react faster in an SN2 reaction than would the tertiary, because the tertiary is more hindered. Okay, so those are the basic terms that we need to look at. So if I'm looking at fastest to slowest, I'm going to automatically put number 3 as the slowest, because it's the more sterically hindered nucleophile. All right, great. So now we're down to 1 and 2, which are both primary. The O minus is attached to a primary carbon. The S minus is attached to a primary carbon. So if we take a look at the periodic table, we have CNOF, Cl, and the sulfur is underneath the oxygen. So what's the relationship between oxygen and sulfur? It is a vertical relationship. So the fact that it's a vertical relationship means that polarizability is the determining factor. And so which atom is bigger, sulfur or oxygen? Sulfur. And so sulfur is more polarizable. And so therefore the sulfur would be a stronger the S- would be a stronger nucleophile than the O-, because sulfur is more polarizable, is larger. And so in this case, I would say that number 2 would be the fastest. Number 1, the alkoxide, would be second fastest. And that would be how we would rank these 3 nucleophiles, taking into account first steric hindrance, and then taking into account the polarizability difference between oxygen and sulfur. Okay, you can go on to problem number 22 that someone asked about. 1 equivalent of sodium methane thiolate. That means basically we have a CH3 with an S- and then an Na+. Just a note about the counter ions in this case. I can't go down to the stockroom and get a bottle of CH3S- off the shelf. It needs a counter ion. And so sodium is the counter ion in this case. What role does it play? In our class, it's not going to play a role. So what I'm really interested in is, this is my nucleophile. And so I'm doing an SN2 reaction. So the question is, when I add it, which product is going to be the major product? So is my S- going to attack this carbon with the bromine attached? Or is that S- going to come over here and attack this carbon with the bromine attached? The bromine in both cases is the leaving group. What's the difference between those 2 carbons? This carbon is a primary carbon, and this carbon is not a tertiary, it's a secondary carbon. So again, going back to to the idea of alkyl halides. With alkyl halides, primary halides react faster than secondaries, which react much faster than tertiaries because they don't react in an SN2 reaction. I should probably be consistent and say a methyl group that reacts the fastest. Why? Because of the steric hindrance on the backside attack. So you can just back the video up, and I've explained that. So which carbon is more sterically accessible? This one. So the thiolate, which is what a deprotonated SH, which is called the thiol, is, it will react with the primary carbon faster than the secondary. So B will be the major product, and major product just means it will be the product that's formed the most. It'll be the product that's formed the fastest. Okay, so again, the difference here is steric hindrance of the primary and the secondary carbons. Okay. In this problem, we're asked which alkyl halides will react fastest to slowest with a nucleophile in an SN2 reaction in a protic solvent, and we want to go which one is fastest and which one is slowest. Okay, so looking at this problem, number 1, I don't think the protic solvent makes a difference, because whether it was protic or in a protic or aprotic, it's all the same. So the protic solvent's just kind of a distractor. It doesn't play much of a role. So in this case, what am I doing? I'm taking a nucleophile again. I'm going to react it with a propyl halide. The nucleophile is going to come in, kick off the halogen. I'm going to end up replacing the halogen with the nucleophile, and then the halide ion is going to be the leaving group. So the real question here is, which of these halogens is the best leaving group? Well, I guess the question first should be, does the leaving group play a role in the rate of the reaction? And that's something that'll come into play in the next chapter. So does the leaving group play a role in the kinetics? Well, what's the rate equation for an SN2 reaction? It's the rate constant times the concentration of the alkyl halide times the concentration of the nucleophile, each to the first power. Is the halogen, the alkyl halide, involved in the rate equation? It certainly is. And so the better leaving group then is going to cause the reaction to occur faster. So what do I have as a leaving group? I've got a fluoride, chloride, bromide, iodide. Leaving group ability is based on what? One thing. It's based on inversely basicity. So whichever one of these halogens is the weakest base, that weakest base is going to give me the best leaving group. And so you may want to go back and take a look at your notes, but which one of these is the weakest base? It is iodine. So we're just going to go right down the line. The fastest reaction will occur with the iodide, which is 3. The next fastest with the bromide, which is 2. The next fastest with is going to be the chloride, which is 1. And then finally the fluoride is going to be the one that reacts the slowest, because fluoride is the strongest base, which makes it the worst leaving group. Okay.